In this video, we briefly overview the algorithm of the division of unsigned integers and the corresponding circuit architecture. As with division of decimal numbers, the binary version requires a sequence of comparisons and subtractions. Moreover, the operation between a dividend and a divisor, both on n bits, produces a result of n bits and a remainder that is also n bits. Let us revisit the division algorithm using as an example the 4-bit division between 10, that is in binary equal to 1010, and 3, that is 0011. The first step determines the most significant bit of the 4-bit division result. To do this, we must compare the divisor shifted left by 3 positions with the corresponding bits of the dividend. If the difference between the selected bits of the dividend and the shifted divisor is greater than or equal to 0, then the corresponding result bit is 1, otherwise it is 0. If the result bit is 1, then in the next step we use the bits of the previously computed difference instead of the original dividend bits. If the result bit is 0, then in the next step we simply bring down the appropriate bits from the dividend. In the example, we can see that the difference between the selected dividend bit, extended with zeros, and the divisor is less than 0. The most significant bit of the division result is therefore 0. Then the next step requires us to bring down the one that was just used. To this value, we append a new bit from the dividend in order to determine the second bit of the quotient. The new comparison with the divisor will be performed against these 2 bits. The result is again 0 because once more the difference is negative. Then, to obtain the third bit of the result, we also bring down the third bit of the dividend and compare it with the divisor shifted appropriately. We can easily see that the value of the difference is now greater than 0, and therefore the corresponding division result bit is 1. Unlike the previous steps, for the next comparison, we no longer bring down the already examined bits of the dividend. Instead, we bring down the result of the difference, which in this case is 10. To these bits, we append the least significant bit of the dividend, and we repeat the comparison one last time. The difference turns out once again to be greater than or equal to 0, and therefore the least significant bit of the result is 1. All the bits computed in this way represent the quotient of the division, while the remaining bits, coming from the final difference, represent the remainder. The discussed example shows that the division between 1010, that is 10, and 0011, that is 3, is 0011, that is 3, with a remainder of 1, represented as 0001 on 4 bits. The algorithm can be implemented using the regular structure shown on the left of the slide. The architecture receives the dividend A, 1 bit per row on the rightmost column, and the divisor B, 1 bit per column, as shown at the top. Each row performs one subtraction and comparison step of the algorithm. The row is composed of identical blocks, each operating on a single bit, whose internal structure is shown in the bottom right part of the slide. Subtraction is implemented using 2's complement arithmetic. The divisor is provided in bitwise negated form, and the blocks include full adders so that each row behaves as a ripple carry adder with a carry-in of 1 applied to the least significant bit. After the subtraction, the block selects either the partial dividend or the subtraction result based on the sign produced by the leftmost block. The remainder appears at the output of the last row, while each row generates 1 bit of the quotient. In particular, each quotient bit is obtained by negating the most significant bit of the subtraction result. A negative result yields a 0, while a non-negative result yields a 1.